In your kit, you received a board that probably has LED and key written on it. This is a multi-purpose board driven by a microchip called the TM1638. If you supplied your own parts, you may have a variation of this board. There's a number of them that use the same driver chip or are from the same family, like the TM1637 or TM1639. They all operate in a similar fashion, which isn't quite standard, but they're still very common, very useful, and quite easy to use. The datasheet is available in the download section, but it is just brutal to try and read through because there's a lot of Chinglish or even, straight up Chinese. Like here, check out what it says about the strobe function on page 2. Initialize serial interface during the falling rising edge, then receive instruction. The first byte as instruction when STB is low. Another disposal would be closed during handle the instruction. CLK would be ignored when STB is high. It's confusing and really of not much help, especially considering just how simple these boards are to use and how cheap and awesome they are. So I've included in the downloads section, ta-da, a 3-page cheat sheet on how to use the board, and then in this lesson we will focus on using it. Now the boards have 3 control lines intended to be used with shift registers, so they are operated in a serial fashion. If you want, you can wire it up with pull-down push buttons and do like we did with the Hitachi display. You can manually send digital signals to control the display. You would simply send 1 bit at a time and simply press the strobe button to lock in the number on the controller chip. But now you're sending 1 bit at a time instead of 4 bits at a time like we did previously. So it'll take forever. Now, these digit displays here are as old as the hills. I remember playing with these in my first electronics kit when I was like 10. It was the Radio Shack 150-in-1 electronics kit. There's the display right there. Memories. Didn't have a clue how any of the circuits worked. I just went by the instructions and hoped they worked. But I still had a lot of fun with it. Anyway, these are called 7-segment displays, as it has 7 LEDs in an array to display numbers. So count them. 1, 2, 3, 4, 5, 6, 7. 7 segments. Now there's usually an 8th LED, the decimal point. Some displays have 9 LEDs. There's a second decimal point on the left-hand side as well. Each segment is typically identified with a letter, and convention labels them like this: A, B, C, D, E, F, and G, and usually a decimal point. Now this board also has 8 discrete LEDs and 8 push buttons, all driven or read by the same controller chip, the TM1638. Now, some boards, like this one, have 2 color LEDs instead of just red LEDs. Now, if you sourced your own parts, you might have a board with either bicolor LEDs or 2 separate LEDs, a green and a red discrete LED. I'll show you how to control the green LEDs as well. Now, while the Hitachi displays had either 4 or 8-bit parallel lines, the TM1638 is serially controlled and is specifically designed to work with shift registers. So you have 2 power lines, VCC and ground, and it can operate on 3.3 or 5 volts. Technically though, as they point out in the datasheet, if the controller chip is hooked up to blue LEDs, these need a higher voltage to even turn on. So that's the real reason for the 5-volt requirement, is to make sure there's enough voltage to turn on blue LEDs. Your boards have red LEDs, which require half the voltage of that blue LEDs do. And so your board should work just fine with a 3.3 volt supply. You then have 3 control and communication lines, typical for shift registers. DIO for digital input-output, the clock, and the strobe. If you have a board with multiple strobe lines like this one, just use strobe 0, which is labeled STRB0. Also notice if you got one of these boards, the pinouts are printed on the back of the board, but these pinouts are the pinouts as viewed from the back of the board, not the front. So you got to mirror the connections when you flip the board over. Now, like the Hitachi, you need to set up and initialize the display first with commands. The commands, data, and shift registers are all 1 byte or 8 bits. I would invite you to experiment by hooking up push buttons on each of the control lines on your TM1638 board and manually send your instructions to the board, just like you did with the Hitachi board initially. Now, while this is fun and highly educational, it is prone to error and impractical for any time other than experimenting. So we're going to use the Arduino to send the instructions and data. Amongst its huge bank of utility circuits that you can call into service from your program, the Arduino microcontroller, of course, has shift registers. This includes a shift out register that you can call with the shift out command. So the word shift out, lowercase s and a capital O, and then in brackets on which pin you want to transmit the data, which pin will be the clock, the order you want to send the bits from the byte, either LSB first or MSB first, and then finally the number or the data that you wish to transmit to the register. If we look on page 6 of the datasheet, we see that the controller chip expects data bit 0 first. So when we set up the shift out command, we send the data LSB first. Now, note you first have to set up the data and clock pins that you want to use as outputs. I also designated a pin for the strobe line and set it up as an output as well. So we first need to send some initialization instructions to our board. We first need to turn the display on and we have an option of setting its brightness. Now, the reason they require you to turn these displays on is because when you power them up, the flip-flops will all take random settings. So the display will show gibberish. It will be completely random lights. With the default startup, the display is off. This gives you the opportunity to load the display registers with whatever you want before the display actually gets turned on, so it doesn't display gibberish. But we want the gibberish for now. Send us gibberish. So we'll just turn it on full blast and not worry about the gibberish. Now, the instructions are on page 5 of your datasheet. It's chart 7.3. However, I have simplified it in the instructions chart on page 2 of the cheat sheet. Now, like the Hitachi display, the commands typically have an upper nibble indicating the command, and the lower nibble contains the settings for the command. So for instance, our command to turn on the display is binary 1000 followed by a single bit which turns the board on or off. And then these 3 bits are for a brightness value of between 0 and 7. Now we want to turn the board on and we want to make the display active, and I personally want it blazingly bright, so I'll put it full power with all 3 bits high. So the number I want to send would be 10001111 or hexadecimal 8F. I'm going to wire my Arduino to my board like this. You can wire yours as you like and then modify the code accordingly. I have pins, I've got pin 8 as the strobe, pin 9 as the clock, and pin 10 as the data input output. I've provided several sample codes in the download section so you can follow along if you want. The first will be the TM1638 step 1 code. After declaring the pins, I set them all up as outputs. Now the strobe pin is an active low pin that tells the board to listen for instructions and data. I'll set it high again upon the completion of every single instruction or data set. Now I'm going to send an instruction, so we need to set the strobe low. I then invoke the shift out command, sending a hexadecimal 8F out to the board. I then set the strobe line high because I've sent all the information I'm going to send. The board will now ignore the data and clock lines while the strobe is high. If I just flash this to the Arduino, it will simply activate the board, turn on everything at max brightness, and because I just powered up the board, the LED control registers have all flipped to completely random highs and lows. So you get complete hash displayed when you turn on the display. So let's send some data out to the displays. Each discrete LED and each 7-segment display has a unique address, and this is shown on your cheat sheet. There's 8 discrete LEDs and 8 7-segment displays. So you have 16 addresses you can write to. You can address all 16 addresses with a single nibble. To set the individual segments in a 7-segment display, we send a single byte with each bit controlling the individual segments like this. So let's say I want to display the digit 3. I need to light up segments A, B, C, D, and G by setting them all to a 1. The decimal point and segments E and F I will set to 0, so they will be off. So our data byte will be 01001111, or hex 4F. So let's start off by writing that data to a single address. Let's write to the 4th 7-segment display. This will be the step 2 sample code. Now we need 3 things. We need the data we want to send, which we just determined we want to send a hex 4F to light up the number 3 on the display. We also need the instruction code to write to a single address and the address we want to write to. So looking up in the instruction chart, the instruction for the single address mode is 44. The address is a byte formatted with the upper nibble as hex C, and then the lower nibble is the address you wish to write to. So in this case, we want to write to the 4th 7-segment display, 1, 2, 3, 4, which has an address of 0110, or hexadecimal 6. So our address byte will be C6. So let's take a look at the sample code 2. All of these instructions are the same initialization instructions we had before. So we set the strobe line low and send the single address write instruction of hex 44. We then set the strobe high again because that's the end of the instruction. The controller is now waiting for an address. So we set the strobe low and send the address C6. The controller chip is now expecting the data byte, so we send 4F, our data. That is the end of the data, so we set the strobe line high. Flash your Arduino, and in amongst all the gibberish, we now have the number 3 on the 4th 7-segment display.